Good afternoon. This time I'm going to cheat a little bit. I made a few notes, okay? Just because it's easy to get lost, because I'm going to be talking about entropy and information, and I wanted to make it as transparent as possible. A difficult thing to do, so I had to sit down a couple of times to organize these ideas. I don't fully have a handle on it myself, but I'm giving it to you as clearly as I've figured it out so far, right? Now, entropy is something mysterious that crops into macroscopic thermodynamics. I'm going to do that from a thermodynamic perspective later. Okay, but I'll have a way of approaching that which is very accessible. I'm approaching it this time from a more statistical or information point of view because I want to be able to calculate it for different things. And we want to be able to change from one set of units to another. For example, from binary units to base 10 units. Bits involve the base 2, 10, the base 10, different, or the base E for natural logarithms, and so on and so forth, okay? So what we're talking about today is entropy and information. Now in thermodynamics, we have a possible change in entropy from S1 to S2. Basically, this quantity is always greater than or equal to 0. Now, the change in entropy is 0 only for reversible processes such as the Carnot engine. A reversible process is one that you can retrace your steps. It's a long and complicated idea. Now, another definition of entropy . S is K log Z, due to Ludwig Boltzman. Now I put the years that Boltzman did this. Oh, this would be around 1870. Okay, Boltzmann's law. It's on his tomb. He committed suicide, I think. Now, R is the universal gas constant. K is going to be Boltzmann's constant. A lot of people write a subscript B there. Na is Avogadro's number. Okay, so this is going to be (1.38 by 10 to the power of minus 3 joule per Kelvin per particle. People tend to leave that one out. It should be put in there. So, this is rather mysterious. We're going to define the following. We're going to define this W. I don't know where it came from. I just came up with this W because I'm going to use this because this K here really just gives dimensions to this piece of information. Yes? So that's number 1. This is concept number 2. This is concept number 3 because it's dimensionless, but really it's not a new concept. W, what is W? Well, what is Z here? Z is the number of microstates in a system, or the number of accessible microstates. Once again, that requires a lot, but for us, it's just going to be the number of microstates in a system. Now what does that mean? Well, Feynman says for all the states that are in the box versus all the states that are out of the box. So if we have a gas, and we'll take an ideal gas. An ideal gas consists of lots of particles with velocities and positions. So all the configurations of the velocities and positions, there'll be a distribution of these velocities, a Maxwell-Boltzman distribution actually. All the possible positions and velocities will constitute the number of microstates. Where are they at any one time? Versus everything outside. So we only consider the particles inside the box, and they're going to be n particles. Now we have the idea that Pv over T is nR, where R is the same universal gas constant, this one, 8.31 joules per Kelvin. And it goes on, there's a few more decimals, I left them out. And this is the number of moles in the gas. So that's going to be the total number of particles over Avogadro's number times R. Okay? Now, of course, this is the same as N times R over NA. And of course that's Nk. So Pv over T is Nk, right? So a formulation of the gas in terms of this, Pv over T is Nkt, and actually we can relate the volume of a gas, the increase of volume, not going to do it now, to the change of entropy as well. So generally we're talking about this whole idea of degrees of freedom. Later on we'll see what happens when the particles are fermions versus bosons and so on and so forth. So that's our first step into this, launch into this. Need my watch. So I'll let you digest that. The next thing I want to look at is, we'll recall logs. Okay, logs. I get that the right way around. The log of a number is the power to which the base must be raised in order to get the given number. Sorry, this should be a y. Let me just check that. Now the power to which 10 must be raised in order to get 100 is 2. So let's see where the variables go. This is the x, this is the base. So therefore then x equals a to the power of 2. So we can say that up here x is going to be a to the power of y. Okay, so on. So the log of a number is the power to which the base must be raised in order to get the given number. Let's just see what else happens. What is log 16 to the base 2? Let's check. 2 2's 4, 2 4's 8, 2 8's 16, 4. We need to multiply the base 2 4 times together in order to get 16. Now the rules of logs are log A times B is log A plus log B, and really that's the main rule, the rest are variations of that. So let's clear the board and continue. Now the reason I'm doing this is because you will see logs to the base 10 and natural logs. Actually, the proper pronunciation for this, natural logs, not quite. It's an Neperian log, okay? What is a log of a million to the base 10? Think, log a million to the base 10 is 6. What is log of 4 to the base 4? 1. What is log 16 to the base 4? 32. Log 32, sorry, 16 to the base 4 is 2. Now converting from one base to another. Now when we see this thing here, we want to write that in a different base because this means k log to the base e z. What is that in the base 10? We will get different units if we go to the base 10. So we want to convert two different things. Okay. I should be carrying this with me. Sorry. So let log x to the base a equals y, let log x to the base b equals z. All right? Therefore, x equals a to the power of y, and I can substitute that in, okay, for here. So x equals a to the power of y. If I put that in here, let's see what happens. That means this b to the power of z. Okay, there it goes. So we can write in log x to the base b is log x, that goes in there, to the base b, okay, wait, let me just go back on that. I screwed up. Sorry. Okay, so we both have values for x. X given by this one and by this one. So therefore then, log x to the base a is log to the base a, b to the power of z, right? Because I just substituted in for the x. Now that's equal to the following. B to the power of z is z times log, because take out this exponent and it goes over here. But z is log x to the base b. So we have a very useful formula that says that log x to the base a is log x to the base b times log b to the base a, and I'm just carrying this with me because we might need it later. So let you get your head around that. That's a useful formula. So, don't need this. We don't even need that formula. Now I'm going to run through different examples, and we're going to work out the entropy for many different situations. So actually do an example first. Log 16 to the base 2 is 4. We said that 1 minute ago. What is log 16 to the base e? Well, it's going to be log 16 to the base 2 times log 2 to the base e, following our formula. Now, log 16 to the base 2 is 4. And log 2 to the base e we can get from our calculator. And of course we know it to be 0.693. So, log 16 to the base e is 2.7726 using that formula. We'll now have another look at another formula. In 1949, Shannon studied information theory, and it's to do with probabilities. He defined the information of a system to be the sum of the probabilities times the logs. Okay, so this is going to be a reciprocal actually. What's the probability of an event happening? Actually now, if I work with a dice, it's much more convenient to use a different base. We'll use the base 6 for a dice. And we can easily convert from base 6 to the base 2. If I have left the base 2 there, that would be the information given to me, the h, would be in bits. But I can write down this following. Sorry, I can't see it. Let's just do the calculation first. Okay, we want to work out h for 6 throws of a dice. For the first case, what is the chance of throwing any one side of a dice? Let's say a 6. The probability of getting a 6 is 1/6, and times, what's the log of that? Now, what's the probability of throwing the next possible outcome in a dice? It's a 5, and then a 4, and then a 3, and then a 2, and then a 1. But each case, it's 1/6. So now, negative log 1/6 is the same as 1/6 times log the base 6, positive 6. Okay? And it's the same for each different case. There are going to be 6 of these ones. Now the log of 6 to the base 6 is 1. And there are 6 possible outcomes for throwing a dice. 1, 2, 3, 4, 5, 6. So if you throw a dice 6 times, you will find the information of all the possible outcomes. Or if you throw a dice 6 times, you'll definitely get a 6. Or you'll definitely get a 5. Or you'll definitely get a 1 or any of the other possible outcomes. Now, what are we going to do? We're going to consider this as the entropy part of this. A minute ago I defined this quantity W. Well, it's going to be our entropy, actually. Well, it's actually proportional to entropy, but the dimensionless quantity, which I divided by the K. K basically is a conversion factor which takes from dimensionless to dimensions of joules per Kelvin. So we have a grid of 10 squares, and we have one particle. And one particle can go in that box, or it can go in that one, or 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 that one. And the question is, how many states are there to this system? Another way of asking that question is, what is Z? Z is the number of states, the number of microstates in the system. This is a microstate, and there are 10 possible microstates. So there are 10 possible microstates, and what is the W? Now we will choose to stick units of base 10 for this setup. If I had a different number of squares, let's say 2, I might have chosen to work in binary units. Just because I can always convert from one set of units to another. So, what is the W? In units of our 10, in units up to the base 10, our W in this case is 10. Now we'll say let there be 2 particles in this system, but they are bosons. So therefore I can have 2 particles in the one box at the one time, stacked on top of each other, right? If I had 100 particles, I could still put them all in the one box. You can put an infinite number of bosons in the one state at the one time. So let's use their bosons. So, fundamental principle of counting. We will use this over and over again. If I have 2 hats, a red one and a blue one, and 2 coats, a green one and a pink one, right? How many different outfits can I make? Well, with the first hat, the red one, I can make 2 outfits changing the 2 coats. If I have 3 coats, I can make 3 outfits. Now take the second hat, I can make another 2. It's a product. If I can do one thing X ways and another thing Y ways, together I can do them X times Y, the product. If if I had three different things to do, x ways, y ways, and z ways, altogether, the product to do them all together would be x times y times z. Now I have 10 ways to put a particle in this box. The next particle, it can also go into the box 10 different ways. So the number of states is 10 squared. This is squared. So therefore then W is log base 10, 10 squared, which is 2 times log to the base 10, which is 2 times 1, which is 2. So in the base 10, W for two particles is 2. Can you see what's happening? I put 10 particles in there. W is going to be 10, no matter what it is. If I have n particles in this system here, to the base 10, W is n. It's the number of particles, right? Or 10 n times log 1. Let's change this grid now and make it a square. Now where we're going with this, we're going to get up to black holes in a minute, okay? I don't want to run out of time here. So I'm going to scrap this and I'm going to change our system. What is the W for one particle? And we're going to use W10. For one particle, there are 100 possible squares to put the particle into. Any one of those, and that's 10 squared. Now W is going to be log to the base 10 of Z, and Z squared is 10. Sorry, I showed that once. So W for this case, where we have a square, 10 times 10 is 2, right? Now you know what's coming next. That's for one particle. I'm going to put two particles in the box. Now we can handle the fermions as well, by the way, but I'm just doing bosons for now. In the next talk I will look at the fermions. So, the number of states for two bosons is 2 to the power of 10. Okay? Let's see why that is. 2 to the power of 10. Okay, for the first boson, I don't know, I'm not sure yet. Maybe I didn't work this one out. Okay. worry, that's not correct. So the number of states, for the first particle, there are 100 possible places to put it. For the second part, there are 100 possible places to put it. So there are 10 to the power of 4 possible rearrangements of particles in here. So what is my Z? My Z is 10 to the power of 4. So for two particles, our log to the base 10 of 10 to the power of 4 is 4 log to the base 10, 1, which is 4 times 1, which is 4. So for two particles in this box, W is 4. Now we know where we're going, right? Two particles, it's 4, or 2 times, I can write it a different way. In units of base 10, so it's 2 times log to the base 10, 10 squared for two particles. Now that's the same as 2 times log 10, which is 1, which is going to be 2n. For that particular particle, 2n is the W. Now let's see what we mean by the thermodynamic interpretation of this. If we want to convert to thermodynamics, well, we can't really, but we can pretend. Well, suppose we have Avogadro's number in the box. So the W is 2 by 6.0, 2 by 10 to the power of 23. Now what is the entropy in units of base 10? Well, it's just K times W. It's just this times this. Now this cancels, and this becomes joules per Kelvin. What is it? Oh, it's not working. Anyway, 1.38 times 12.04, it's approximately 12 8's 96, 12 3's 36, and 45. 12 1's 12 and 4 is 16. So approximately 16 joules per Kelvin is the entropy associated with this particular setup, with the box. Now what if things were our fermions? My calculator's gone dead. Now I have a lot more examples coming up with this, by the way. I'm also going to do examples where I convert to the base 2. That's in base 10. Now we could convert that to the base e, right? Now if I go log x I could go log x to the base e, in other words log of this is that. So let's just do this. Oh, my calculator doesn't work. I have to wait for the next class. Okay, so you get the picture. We're learning how to handle and manipulate entropy, right? Rather than just looking at Boltzmann law and walking away from it. These are all situations, and I have more to come. I didn't do them very well in this one. I'll come back again and do it a little bit more clearly. Okay, and I'll also look at a little bit more Shannon's formula. That'll do us for this one right now. Yeah, so what's log 10 to the base e? I don't know. I have to find a new calculator. All right.